University in Kingston, Canada, and had a PhD in astrophysics at the University of Victoria in Canada also. After that, she joined a postdoctoral fellowship at the University of California, Santa Barbara, works with the La Cumbres Observatory Global Telescope Network. And then she moved to a senior postdoc fellowship at University of California in Berkeley. Then 5 years ago, she joined the LSST data management team at the University of Washington. And she's doing an incredible job in moving on the collaboration. She's an expert on supernova type 1 rates and environment. Welcome, Melissa. The stage is yours.
Wonderful. Thank you so much, Mariano. Thanks for inviting me and having me here today. Yes, I work for the data management team for Rubin Observatory as a science analyst, which means that I try to really understand the science that people are going to be doing with Rubin Observatory and the LSST data and make sure that the data products that we're producing are going to meet those science needs. And then I've also recently taken on leadership of the community engagement team as we move towards operations and we start having people sort of coming and starting to use the Rubin Observatory services like the Reuben Science Platform that I'll tell you about today, and as we head into commissioning and we start to have real users. So I'm in charge of the team that tries to engage people in their science, understand their problems, and make sure that we're enabling science as best as possible. So today I've prepared for you a talk about Rubin Observatory that's very introductory level. I see there's 40 of you there. I know Argentina is sort of just getting its in-kind contribution team up and running. And so I'm not sure really what everyone's background is with respect to Rubin Observatory. So it's quite simple. We're going to cover a lot of ground, cover a lot of jargon, terms, ongoing initiatives with the community. And so do feel free to pop questions in the chat as we go, or raise your hand and maybe I'll be able to see it, or just unmute and ask questions as we go. Because I pitched it so introductory, you might have lots of follow-up questions and want to ask like more complicated questions, and that is totally fine. So with that, there's also one more thing I wanted to say before we get started, and it's that the Rubin Observatory data products, like the data itself, the data products that Reuben will make, and the access, the Reuben Science Platform, the way to access the data and analyze the data, all of it is proprietary, so available to individuals in the US and Chile, and then also to named members of international teams. And so Argentina has a team, but in order to use a lot of the data I'm going to talk about today and also use a lot of the tools and services, you need to be a member of that team. In some cases, some data products are publicly available, and I'll try to make that distinction as we go, just in case there's people who are here on the call, but who might not be part of the Argentinian team. I wanted to make sure that's really clear. So that those kinds of questions might come up as we go today as well. So with that, to start us off, let's begin with the science pillars, so the motivation for Rubin Observatory in the first place. Rubin Observatory has 4 main science pillars. 2 of them are presented here on this slide. One of them is probing dark energy and dark matter, so doing things like weak lensing, BAO, looking at supernovae for dark energy constraints, quasars, large-scale structure, all of that kind of thing. The second science pillar is the solar system, so taking a full inventory, as full as possible, of the solar system. That includes finding like almost all of the near-Earth objects, and especially the potentially hazardous asteroids that are on a collision course with Earth, finding all of the comets, looking at Trojan asteroids, and trans-Neptunian objects, so the small objects in the outer solar system, as well as we now know, interstellar comets and asteroids. The third science pillar is exploring the transient optical sky, so looking for things like supernovae, variable stars, transiting exoplanets, gravitational microlensing, active galactic nuclei, and also tidal disruption events. Basically anything that changes or varies with time is a better understanding of those objects is one of the 4 core LSST science pillars. And last but certainly not least is mapping the Milky Way. So looking at the structure and evolution of the bulge, disk, and halo, getting a census of dwarf satellite galaxies of the Milky Way and also their tidal streams, looking at stellar evolution in the Milky Way over time, making a three-dimensional dust map, and looking at hypervelocity stars within the galaxy. So really mapping out the entire structure of the Milky Way farther than ever before. So those are the 4 main science goals that motivate everything about the design of Rubin Observatory, its camera, and its survey. And so it turns out that if you want to make major science advances in these 4 areas, the thing that you build is Rubin Observatory. So Rubin will be located on Cerro Pichon in Chile. It's got a 8.4 meter primary mirror in diameter and a camera that will be 9.6 square degrees field of view, and it'll have 6 optical to near infrared filters, U, G, R, I, Z, and Y. So this is a picture, I think, from earlier this year, where you can see the main building of the observatory is built, and now the dome is starting to be covered. I think the dome is now fully covered, so this picture is a little bit out of date now. And once it is fully built and the telescope is installed and its cameras, the Rubin Observatory will execute the 10-year Legacy Survey of Space and Time. That's the new LSST acronym. And that survey will be covering 18,000 square degrees of the southern sky. It will do approximately 825 visits per area of sky over that 10 years, where each visit is about 30 seconds. The single image depths that you get from a single visit, like a single 30-second image in UGRIZ, I have on the slide here. So about 24.7 in R. And then once you stack up all those images over the 10 years, you're looking at, like, for example, an R-band depth of about 27.5. Everything about the observatory design, the camera, and the sort of the fiducial type of survey that you do with Rubin to hit your science goals is all described in Ivizek et al. 2019. Basically it's the science motivation to scientific design paper that you can find a lot more in. If you're looking for things like key numbers and you want to go back and you want to find this 18,000 square degrees and these depths and stuff, they're in the paper, but they're also on the website at lsst.org/scientists. You'll find, I'll put it in the chat. I believe that's the right link. You'll go there and you can find a key numbers page that has all the little details, like the plate scale of the camera and all the little things that people usually want to know about an observatory and its telescope. So I'm going to just delve a little more into the survey strategy that will help Rubin meet its science goals. So what we call the baseline survey strategy was designed to meet the basic requirements of Rubin Observatory and achieve the core science goals that I just mentioned of the LSST. And this baseline design is like a fiducial survey or like a nominal survey that we know will achieve the basic science goals of LSST. So to do that, we have what's called the wide, fast, deep area, or WFD, but most people refer to it as wide, fast, deep. And it should cover at least 18,000 square degrees, as I mentioned, have that number of 825 visits over 10 years, and also do a same night, same field revisit pairs to better find fast moving objects. In addition to this wide, fast, deep area, the additional areas that you have to cover in the baseline survey strategy are at least 4 deep drilling fields, also some special areas like the North Ecliptic Spur, which you add on to your wide, fast, deep area. That's motivated by finding solar system objects. You also do a little bit of a different observing pattern in the galactic plane, where the fields are very crowded in order to satisfy galactic plane science. And then also you can see down at the bottom, the South Celestial Pole, doing some coverage down at the pole is added on to the wide, fast, deep survey area. And all of these sort of areas and surveys together make up the baseline survey strategy. So This baseline was, as I mentioned, just developed to make sure that, you know, LSST can meet its main science goals. But from there, how to optimize the LSST to maximize scientific return is a very open question. And I kind of want to get into some of the jargon and some of the things that people are working on to really optimize the survey strategy. So some of the open questions about survey strategy when we're talking about the wide, fast, deep, or which is also sometimes called the main survey characteristics, the things people are thinking about are the footprint. So how should we define that wide, fast, deep area? Where should that 18,000 square degrees, what should it cover? How much of the galactic plane and the dusty area should be avoided versus, you know, going further in the north and south? Another thing that people are really thinking about a lot is cadence. So how often wide, fast, deep fields are revisited. That gets you sort of your light curve sampling on your transient objects. That cadence applies both within a night. So how, what is the time separation between the revisits that you need to do in order to find fast moving objects versus the cadence, you know, do you come back to a field every 2, 3, 5 nights in order to fill in your transient light curves? Another open question is about the filters. So what is the optimal filter distribution between the wide, fast, deep fields? And by that, I mean, how much time relatively do you spend in U, G, R, I, Z, and Y, respectively? That has a lot of implications for example, photometric redshifts and a lot of the deep imaging science. And another question, of course, is about related to filters is the colors. So what are the optimal intranight filter pairs if you're coming back to the same field in the same night? Do you do it in the same filter, or maybe you do it in a different filter so that you can get like a color for slower evolving transients? There are also lots of open questions about the deep drilling fields and the mini survey fields that I mentioned, such as adding other deep drilling fields. What's the size of those other mini survey areas that I mentioned? And then of course, all the same questions for the wide, fast, deep about footprint, cadence, and filters and colors would also apply to the deep drilling and the mini survey fields. And then on top of this, we have potential gravitational wave target of opportunity observations. And so there's lots of open questions about how frequently you want to execute TOOs. What do you do during a TOO? How does it affect your main survey? All these are open questions that are being explored by the science community in trying to optimize the survey strategy for the LSST. So to address these open questions, the Rubin Observatory LSST scheduler team is generating a wide variety of simulated surveys. We call these operations simulations, or OPSIM is a term that you might hear a lot, where one OPSIM run is basically a simulated 10-year survey for a given strategy. So an OPSIM run consists of input, that is the strategy parameters like the area, the revisit rate, all those open questions. So you like pick answers for those open questions that I just mentioned and make them your strategy for a given OPSIM run. And then the scheduler team generates 10 years of moon cycles, weather patterns, target of opportunity, observations, all that kind of stuff. And then also generates the schedule, so 10 years worth of observations based on the input strategy and the 10 years of weather that you made. And then there's an output from every operations simulation run as well, which we call an OPSIM database. That's basically just a whole set, 10 years worth of simulated observational metadata. And so we have these OPSIM databases for lots of different strategies now. And to help scientists evaluate these simulations, the LSST scheduler team has built the Metric Analysis Framework, or in short, it's MAF, which is a code package that manages the derivation of science results from an OPSIM database. So MAF and Metric Analysis Framework are terms that you might hear as you start to work with Rubin Observatory, where a metric is a measure of scientific performance, such as the number of detections of a certain type of object or the 10-year co-added depth, or anything from this operation simulation that can be turned into like a scientific prediction for how well that given strategy is going to do for a given type of science. So this gives you sort of lots of the lingo and the language about how people are approaching optimization of the survey strategy. And as a timeline, in last year, the LSST formed the Survey Cadence Optimization Committee, the SCOC. This is a committee that will stand for the duration of Rubin Observatory. It consists of 10 people who represent the LSST science community, and their whole goal, they are charged to recommend specific survey cadences be adopted. So their charge is to consider input from both scientists and Rubin staff who have written metrics and analyzed the different OpSim databases and sort of come forward with a single observing strategy that will sort of do the best or optimize LSST science in general. So earlier this year, in March of 2021, cadence notes were submitted to the SCOC, so that's scientists like me writing a short couple-page statement about what type of observing strategy will or wouldn't work well for my type of science. So that call went out, and right now I think the SCOC is still looking at all of those cadence notes and will later this year make some recommendations about what an optimal cadence, what an optimal survey strategy might look like, and also whether new operations simulations need to be done so that scientists can analyze, continue to analyze different options for a survey strategy. So that kind of covers what I wanted to say about survey strategy and the ongoing effort to really optimize how the LSST will be run. And before I move into data products, I'll just sort of pause for a second in case there's survey strategy questions. Okay, I don't see any hands up or anything in the chat, so let's move on to data products. So of course, this giant survey that we're going to do is going to create a lot of data. This slide is sort of like a all-in-one look at the Rubin data processing and the Rubin data products. So we can start over at the left with the raw data that comes off the telescope every night, about 20 terabytes per night. And that raw data will be sequential 30-second images that cover the entire visible sky every few days, as we just discussed. So we start with the raw data, the raw images. And the first thing that happens to a raw image is it goes into the prompt processing pipeline. And that prompt processing does difference image analysis right away. So it takes the new image, and you have a template image that was made before, and it subtracts the template from the new image. So now you have what's called a difference image. And then you do source detection in your difference image to immediately get a list of everything in that image that you just took that has changed in brightness since the template. So you have a difference image magnitude. And then all the sources that were detected in that difference image become what's called an alert and are released publicly worldwide for people to analyze. So, and all of this happens within 60 seconds. So what I just said sort of follows the top of the slides here, where the first image, it goes into the prompt processing pipeline, and within 60 seconds, nightly alert streams are issued for any objects that were detected to have changed magnitudes from the template. So that's the sort of the prompt processing that happens at the same time as, so of course, in a difference image, you'll detect the things that have changed in magnitude, but you'll also detect things that have moved as a new point source at a given location. And so linking between point sources at a new location into solar system objects, that also happens sort of on a daily cadence. So the time scales you have here are the 60 seconds for the alerts to go out from difference image sources. And then within a day, you have the solar system objects database updated with, objects that are linked together that were detected in the difference image, as well as within 24 hours, the So the nightly alert streams go out to the community brokers, but LSST will also have databases of all of the sources that were detected in the difference images. And those will be available within 24 hours. So all of that is sort of happening in real time as the survey progresses, so that scientists have access to the results of difference image analysis in real time so they can do their follow-up and that kind of thing. And then also, of course, on a yearly basis, there will be an annual data release, data products, and that's where you'll have reprocessing of all of the images with the prompt pipeline as well as the annual data release pipeline. So you have basically it's the annual data release, so it has all the individual images, the stacked images, so the tenure, all the stacks to date, and then also has all the individual images, the catalogs of data of objects detected in different images, also in the individual images, and then also in the deep stacked images. So it's basically everything is reprocessed and released on a yearly basis. And so whereas the alerts that are going out in 60 seconds will go to community brokers, all the other data products that are available in 24 hours or on an annual basis will be available through the data access centers in Chile and the US, which users will access via the Rubin Science platform, and that's what's across the bottom there. So the Rubin Science platform is it's a browser-based way to access and analyze the data that provides next to the data analysis. So you log into the Rubin Science platform and do your analysis there because you can't download these massive data products. So there's a couple of acronyms that come out of this sort of overview of the data products. One of them is DIA, which stands for Difference Image Analysis. DAC, or DAC, is the Data Access Center. And then the other acronym on this page that I didn't really mention is an API, Application Programming Interface, and it's one of the 3 interfaces that users will have to interact with the data. And that's down the bottom in the blue square there, where the Rubin Science platform will have a portal aspect, notebook aspect, and an API aspect. So this was like a very, very condensed view of all of the data products and the processing pipelines, which are all, if that's something you do want more information about, it's the data products definitions document. So the link at upper right is the place to go. And that's at LSST/DPDT. And that contains like every single measurement that would be made based on the LSST data that would be available to people. And so I just want to flip to this slide because it's just another way to look at the data processing and the data products, where again, we have the prompt processing pipeline that I talked about that produces alerts within 60 seconds and updates the prompt products catalogs and also the imaging database within 24 hours. It has sort of all the different aspects of the prompt data products that I just talked about here on the left. And then in the middle, the annual data release processing with data releases every year, starting, I should mention, at half a year. Data release 1 will actually be the first half year of data, and then data release 2, the first full year of data, and then yearly after that. And all of the different types of images and catalogs that will be in the data release. And then I should mention also there's a third type of data processing that we call user processing. So basically, although most of the LSST science that the science community will want to do will be satisfied by either the data products available from the prompt processing or the data release processing, of course, there will be other things that people will want to do. And so we kind of call all other user processing user-generated data products. So that's anything that's, that users have used the LSST science pipelines to create. And like everything that I've been talking about so far, all of these Rubin data products are subjected to the Rubin data rights policies, which I mentioned right at the start. So yeah, I think I will pause here. And if there's any questions about the data products, like will Rubin produce X that I need for my science, that's a good question that you can ask here. Yeah, I see a raised hand. Go ahead.
Hi, Melissa. Just a question about the alert products. So every 60 seconds, let's say at the beginning of the night, you take your template image and you compare the second image with that template, right?
The templates are like from the last year.
From the last year, okay. And then if a source gets bright during the first image, then you have an alert 60 seconds after, right?
Yeah.
Then the second, third, fourth images are still compared with that template taken from a year before, and then the alert gets upgraded if there is anything that is evolving. Or, I mean, my question is, do you have, for the same source, many alerts during the night?
Yes. Yeah, if you were, for example, doing a deep drilling field where you're returning to the same location and you're doing image after image there, every new image creates a new difference image, and then you have the new sources in that difference image, and every single source in every difference image gets one alert packet. Yeah.
Okay.
Yeah, exactly. So that's how brokers will have to, they will get all these alerts coming in, and then they'll have to associate them together so you can build a light curve from them. Mm-hmm.
Okay, thank you.
Okay, looks like there's no other questions about the data processing pipelines or the data products at this time, but you can definitely ask them later as well. So the LSST will cover a third of the sky each night and detect billions of stars and galaxies and millions of transients, variables, and moving objects, and create all of those data products that I just mentioned from the two data processing pipelines. And altogether, this makes an unprecedented data volume with a complexity that requires a lot of preparation to maximize scientific return. And also, in addition to like requiring preparation, you need sort of the old tools of just sort of downloading a catalog and playing with it on your own computer. It's not a model that's going to work for the future. So to meet this sort of unprecedented data volume and complexity, we'll also need sort of a new way of accessing and working with the data and the data products. And that is where the Reuben Science Platform comes in, which I touched on briefly before. So since it will not be possible to download the entire LSST data set, scientists need a venue for next to the data analysis. And for that, we have the Reuben Science Platform, which is a set of integrated web-based applications and services that will be running at the Reuben Observatory Data Access Centers, the DACs, like I mentioned. So the RSP, Reuben Science Platform, the RSP will include tools to query, visualize, subset, and analyze the full LSST data archives in a stable software environment that's located next to the data. It will also contain for users storage space, compute resources, and remote access options. So really the idea is to sort of provide everything that scientists need in order to analyze the data products. So you don't have to install any software on your laptop. You don't need to, for your local department, to buy a big server to host all of this data. None of that should be necessary. You should be able to just log into the Reuben Science Platform and do your science there. And for doing your science, there's three main aspects that you would use in the Reuben Science Platform: the portal aspect, notebook, and API aspect that I mentioned before. And I'm going to show you just in a little more detail what these different aspects look like. So first is the portal aspect. This is a screenshot of what it looks like when you're working in the portal. The main sort of purposes or use modes for the portal aspect are to explore and to analyze image and catalog data sets, to also sort of view and interact in a live way with the LSST images. You'll be able to sort of query and subset data catalogs using sort of a graphical user interface or query languages, whatever you're comfortable with. So if you're not really a SQL or ADQL user and you want to fill in boxes, search boxes instead, there's both options there for you to query and subset the data, and then also to make your plots right in the portal aspect. So you can make your scientific graphs, and you'll be able to link data selection across plots and images, which is kind of what this screenshot is trying to show you, that you have sort of one selection of data products, and then you can plot it and look at it in multiple ways all at once. So that's also what makes the portal aspect so good for discovery. It's a way to sort of poke around and change your plot parameters, change your search parameters, see how things change sort of in a live and dynamic way. The other aspect of the RSP will be the notebook aspect, and this is basically just a Jupyter Hub portal. So if you're familiar with Jupyter notebooks, the notebook aspect would look very familiar to you. So some of the main use cases for the notebook aspect, as you can see in the two images that are here, you can also, of course, do things like subset, query the data, and make your plots. You can do a little more sophisticated things. For example, if you have your favorite plotting software that you can load into your notebook like Bokeh, and you can make really sophisticated interactive plots. You can do that in the notebook aspect. It'll provide, one of the really nice things about the notebook aspect is that it provides very stable user environments with pre-installed libraries, so you don't have to set up or maintain your code environment. So it'll automatically include all of the LSST science pipelines and a lot of the most familiar code packages like AstroPy and SciPy and all that kind of stuff. But of course, you can also still install your own tools as needed. And both the portal and the notebook aspect, where the notebook aspect is probably what you're going to be using if you want to reprocess the data, for example, and make user-generated data products. For example, making monthly stacks instead of annual stacks of the images to try and search for like long duration faint transients, for example. You're probably going to be doing that kind of thing in the notebook aspect. And the Rubin Science platform will provide the compute resources for that kind of reprocessing as well. So I wanted to get into a little bit, to tell you a little bit more about what alert brokers are, because I did mention before that it's the prompt products, like the images, the difference images, and the catalogs that come from the prompt processing, and then also the annual data release data, all the images, stacked images, object catalogs, and so forth. All of that will be available through the Rubin Science platform. But the very first data product that I mentioned were these alerts, this stream of alerts that goes out within 60 seconds. And the Rubin Science platform is not going to be how users would interact with that data product. Instead, if you're interested in really real-time stuff with transients and variables and moving objects, you're probably looking at using alert brokers instead. So I wanted to sort of go through some of the language around alerts and brokers in a little more detail. So first we have this concept of an alert, where an alert is an ASCII file of information about a single difference image source that is detected with a signal to noise ratio of greater than or equal to 5. So it's one alert per detection in a difference image, where these difference image sources include transients, variables, and moving objects. So alerts that are based on a new image are streamed to alert brokers within 60 seconds of image readout, as I mentioned. And alerts packets are world public and have no proprietary period, so you don't need LSST data rights in order to use them for your science. A broker, on the other hand, is a software system that will ingest, process, and serve to the astronomical community alerts from Rubin Observatory. A lot of brokers also serve alerts from other surveys. For example, ZTF, this Wiki Transient facility, is already producing alerts and streaming them to brokers. Typical broker functionality includes, for example, cross-match association with archival catalogs. So a new source comes in and maybe you want to see if it was ever detected in GTF, for example, or cross-match it to archival catalogs like a PanSTARRS catalog, for example. Brokers also do things like prioritize objects that need follow-up observations. So they're the ones that are seeing the alerts come in, they apply filters to them, and they could say, for example, this transient is red and it's rising particularly quickly. This science goal needs to get this kind of spectrum for this object, in the next 2 days. So doing that kind of real-time analysis and prioritization of follow-up. And then also on a longer term, some brokers do photometric classification based on light curve analysis. So, they collect the alerts that come in, build up light curves, and can say, oh, this looks like a type 1a supernova or whatever. So that's what an alert is, what a broker is, and what the broker does. And one other typical broker functionality that I should have put on this list is to provide user access to the alerts. So users can usually query the database of alerts. Users can set up their own filters to get like a notification of when there's an alert either in a certain area or an alert that has a given set of parameters, like a certain rise rate or once it starts to fall or sort of whatever it is that you need for your science. You can set that up in a broker. The exact alert contents, I have a little list here, but they're also fully described in section 3.5 of the DPDD. The alert contents include like an alert ID, of course, all the measurements from the new image, from the new difference image, like the coordinates, the magnitude, shape of the PSF, all of that kind of stuff. Every alert also contains a 12-month history of detections at that given location, if they exist. And then also association with variable and static sky objects from the most recent annual data release, as well as image cutouts, so little 6x6 arcsecond image stamps at the location of the transients. That's what's in an alert. If alerts and brokers are something that's interesting for you for your science, you can find a lot more information at lsst.org/scientists and specifically /alert brokers. And in particular, this website has the list of alert brokers that will be receiving the full stream from Reuben Observatory, most of which are already running right now on CTF alerts. So you can go get an account with Alersi, Ample, Antares, Finklasair, or the PIT Google broker and start looking at their functionality and using them now. There's no need to wait until Reuben starts. So that sort of finishes the alerts and brokers section of data products. So I'll just pause again here and see if there are more questions. Will RSP tools be available for people outside LSST collaboration after the data becomes public? No. So the two questions here. So the proprietary period for LSST data products is 2 years. And so after that, the data does become public. But at the moment, there's no plan to serve that post-proprietary public data via the RSP. So the RSP tools and access to the Reuben Science platform itself is limited to data rights holders. Yeah. You're welcome. Okay. So we talked a little bit before about how the science community is working to optimize the survey strategy for the LSST, but I did want to talk a little bit more about why and how people are preparing for LSST now. So as you've kind of seen from this introductory talk, the scope and potential for science with Reuben Observatory is like as enormous as the unprecedented volume and complexity of the LSST data products. So correspondingly, the technologies, methodologies, policies, and collaborative strategies for research with LSST are evolving to meet this challenge. So people are doing things now like assembling precursor data sets, generating sophisticated new algorithms to use on the LSST data. They're building software infrastructure, establishing policies for collaboration in the future, and also investigating synergies with future facilities such as Euclid and the Roman Space Telescope. So all of this is kind of happening now. People are getting involved and preparing for LSST. And the main sort of venue for that preparation is the LSST science collaborations. And so this is sort of a one slide, like an exciting and dynamic single slide about the main goal of the science collaborations is, to leverage this unprecedented data volume into multiple science goals and do the preparation now in order to make use of the data once it's, coming in the first year and beyond. So there are 8 different science collaborations. These are all independent of Rubin's Observatory. They're all self-managed teams that work together in different ways. They all have their own charters, their own members, their own policies, and their own goals. And sort of this represents the 8 of them. So active galactic nuclei, dark energy, informatics and statistics, galaxies, transients and variable stars, stars, Milky Way and local volume, strong lensing, and solar system are the 8 topical science collaborations that currently exist. One of their main focuses, or like the main focus, is on science preparation and doing training and support for their members. So this is just sort of like a single slide of examples of some all pre-COVID live meetings where people get together to work on various projects together or learn how to use new software or make plans for analyzing operation simulations, all that kind of stuff. Very active work going on in the science collaborations. They also provide expert advice and analysis to Reuben when needed. Together they fundraise for their teams and for their projects. They're very busy developing and implementing research inclusion practices. They work together to train, educate, and engage the science community. And a big one also is collaborating on software development. So making all the analysis tools that they're going to need in the future to deal with LSST data. So science collaboration members enjoy and benefit from a supportive collaborative environment that places them in the best position to generate science with Rubin data. And you can find out how to join at this website here, which I'll just put into the chat for you. So that's where to go if you want to join one of the science collaborations. What am I doing for time? I'm going to skip this. So if you are interested in getting involved, joining a science collaboration is one of the best ways. If you want to sort of get involved and really start working with people and writing software and doing precursor surveys. If you're looking for a little bit of a less sort of intensive, more casual involvement, like you just sort of want to keep tabs on what people are talking about and what's happening and maybe have a place to go to ask questions about Rubin Observatory, then the Rubin Community Forum is the place where all of that kind of stuff is happening right now. So you can go, as I'm talking, to community.lsst.org, and you'll find this landing page here, where first I'll mention that this top banner here, where it says expand, I don't know if you can see my mouse, I don't think you can. Oh, yes you can. Where it says expand, that will tell you more about the community forum itself and how to navigate this website. But otherwise, when you come to the main page of community.lsst.org, you'll see on the left is a lot of categories for different discussions that are going on. And then you'll see over here on the right, this is just a chronological list of the most recent topics that people have been posting or commenting on. And so I want to draw your attention to 2 categories in particular that would be of greatest interest to you. One of them is the support category here, which is dedicated to questions from active users of the Rubin Science Platform and the LSST Science Pipelines. This is where people go to ask questions, like when they're having trouble using the LSST Science Pipelines. They come here, they can post their question and get answers from Rubin staff. The other most interesting category for you will be the science category, and this is for all questions and discussions related to LSST science. And in particular, I wanted to point out there's a data Q&A category here. So any of the stuff that I mentioned today about data products, prompt processing pipelines, what's contained in alerts, what's contained in the catalogs, what are the measurements going to be for objects in stacked images, for example. Any questions that you come across like that, it's the data Q&A category here that's really intended for anyone, anywhere, to be able to post their questions and ask questions about the LSST data products. And I actively monitor this category along with other people from other Rubin Observatory staff, and we try to make sure that any questions posted in there are answered pretty promptly. So things you need to know about Rubin, that's the place to go. You'll see also there's a category for survey strategy. So if you're interested in participating in any of that optimization that I talked about before, that's the category that you'll want to head to for that. So that's a great place to come and look for answers to questions that you have by either posting your question as a new topic in any of these categories, or you can see up here there's a magnifying glass where you can search the entire community forum for what other people have been talking about as well. So just to wrap up, this is sort of a final list of links that I mentioned throughout the talk. The best way to get involved is to join a science collaboration, but also the Rubin Observatory Community Forum should be very useful to you. And then down here, I have all the links to resources and publications like the lsst.org scientists page, the science book. I forgot to put the data products definitions document on this last slide, but I'll put the link in the chat because it's really just, it's a big document, but it's easily searchable. Easily searchable. So if you have any questions about the contents of this talk, or especially things I didn't cover that you were hoping to find out more about, I'd be very happy to try to answer those questions, or just hear about what Rubin-related science people are interested in Argentina, just to try and get a sense of what your team is going to be working on and how I might be able to help you in the future as data management science analyst or as a community engagement team lead. So yeah, so I'll wrap it up there. Thanks.
Thank you so much, Melissa. There are some questions.
Yes, Dante, I see your hand is up.
Yeah, thanks, Melissa, for the talk. And I have a question. We are very interested in study large-scale structure and dark energy. So we have to design some strategies to find structures in this data with photometric redshift and everything. And I think that the most important difficult for us is to access to large volume simulations to have something similar to what we are expecting to get with the LSST. So my question is, you mentioned three channels, or I mean three forms to access to the data with the portal and the Jupyter Notebook, and also you mentioned some kind of API. This API will allow to access other data, just like hydrodynamic simulation, cosmological simulation, I mean, not only access, but also access to resources to compute things. I mean, to, I don't know, log in a cluster and run C code. I mean, something that with high performance to access this kind of products. I'm not sure if I'm explaining myself clearly.
Yeah, so let me just pop back to so the people. Right, so we're talking about the Reuben Science Platform. I think you're asking about more details about the capabilities of the Reuben Science Platform.
Yeah, because I mean, for analysis of the large scale structure, you need some time to have access to the to simulation high resolution, just to find to test, for instance, a model for galaxy formation, and then you need to make a strategy, I don't know, to study galaxies inside voids, for instance, and then in that case you need to manipulate your simulation data, and in the case of this survey, this simulation data will be, I don't know, much more than we are able to simulate in the clusters here in Argentina. So I'm not sure if Rubin is going to give this kind of support. I mean, to give access to supercomputers or give access to large simulations.
Yeah, I think the answer to your question is no, because the Reuben Science Platform only serves LSST data, and it makes so the compute resources that the science platform is built on, like most of them go to generating the data products, and then some fraction is reserved for users to do their analysis and to, reprocess, not maybe the entire data set, to reprocess regions or certain images. And I think that's, one, not nearly enough for what you need to do like major cosmological simulations. And then two, because it's only serving Reuben data products, Reuben has no plans to sort of serve cosmological simulations. So that's all things that the science community would be doing separately, which is part of the reason why there's so much early preparation work going on right now for things like that. Yeah.
Okay, and I have a second question, if I can. Suppose that when I for instance, I'm interested to find voids in the distribution of galaxies in LST, in Rubin survey. So, if I develop a strategy to find these structures, and then all the data that is involved in a publication or in a release of these catalogs, it should be publicly available. Also, the simulations and all the things that I use it to make. I mean, there is some standard for science. You are asking to the people that participate in the survey to make everything available for the community or or publicly.
Maybe I'm not exactly sure what the question was in there.
The question is if you are if Rubin is asking to the people to make all the aspect of their research open to the community and to the. I mean, when you produce a data, you have to make all the code public and the data also.
No, there is no. There's no sort of have to. So if you wrote code, you can absolutely write proprietary code that analyzes, and you can keep it in the Reuben Science Platform, but it would be in your account space, and only you would be able to see it. Only you would be able to see the data products that you make, and you can write your publications based on that. So that part is still, Reuben Observatory is not going to be forcing anyone to make proprietary code public or make user-generated data products public, but they will provide there will be that option for you. So if you wanted to if you make a catalog and you wanted to share it with people, there will be ways to do that within the Reuben Science Platform, but not mandatory, no.
Okay, thank you.
Did that answer your question? Okay.
Yeah, I try to ask that. You perfectly
Okay.
answered.
Cool.
Thank
Thanks.
you.
Yeah. I think Mariano is the next with his hand up.
Yes, just for answer the question by Dante. Maybe the resources that you're looking for are from not from Rubin's, but from the specific scientific collaboration that you're thinking. That is DESC. DESC has a lot of resources, computational high-performance computer. I think that in Livermore National Laboratory, which comes on which servers in this portal. And when you are working inside the desk collaboration, you have access to huge supercomputers where the simulations were done and where the kind of analysis they are suggesting on large scale structure could be done. That is the reason why we are trying to participate, have data rights, and work with the scientific collaborations. That you have this kind of products that they know the real data, but they are related with the analysis with the real data using simulations and this kind of stuff.
Yes. Thank you for bringing up that DESC is really the answer to Dante's first question. Yeah, that's a good point.
Thank you.
Yes, Jose has his hand up.
Hi, Melissa. Thank you for this great talk. I have a question, but I don't know if it's a question. In the initial part of the talk, you comment some about of this simulated runs data, and I'm very confused. This data were running or will be run, and the question is if exists some kind of access of this simulated data. I I ask this because, in particular, I don't have very large experience with observational data, and I have a very great interest in to the training with this simulated data, thinking if prepared with when we have the real observational data, have very experience of the control of this kind of data, scripts, or others.
Yes, I think I understand the question you're asking, and I think you were referring to the operation simulation that I mentioned. But these simulations don't actually simulate the data. So they don't simulate images or catalogs or anything astronomical. They only simulate, they just simulate the survey strategy. So they'll sort of, they simulate a database of like dates that exposures were obtained at, like dates, locations, and filters. So this is only simulating a strategy and not simulating images or any astronomical data in any way. And I think it sounds like you're looking more for simulations of LSST-like images and with astronomical transients and objects in them. And for that, this actually, again, is a DESC. DESC is the answer here again, because they have been doing a lot of simulations of LSST-like data. And in particular, their data challenge 2, DESC data challenge 2, or DC2, is a big simulation of like 300 square degrees of the sky and 5 years with LSST-like images. So I think that's more what you're looking for. That's something that's available to DESC members, but also they've made some of their catalogs publicly available, which I can put the links in the chat for that later. But if you're looking for images, I think the images from that simulation aren't publicly available yet. But the other option to using simulated data is just to use data from precursor surveys like Zwicky Transient Facility or Pan-STARRS, or any data from the dark energy camera at CTIO. That would also give you a good starting place for LSST-like survey images. Is that kind of getting towards an answer to your question?
Yes. Thanks for this. This information of this data and this website. I checked this and thank you.
Okay. Also just gonna pop in the chat a link to a post on community.lsst.org, the community forum, that's says a little bit more about what the desk, the Dark Energy Science Collaboration, has released publicly from their simulation. If that was interesting to you, it's a place to start. Oh, I should also say, actually, that Rubin Observatory is using some of the desk's DC2 simulated images to run something called Data Preview 0. And Mariano is participating in Data Preview 0. And it's basically just serving some of these desk simulated images in the Rubin Science platform. And there will be another call for people to participate in Data Preview 0 next year. So I didn't include that in my talk today, but it's Data Preview 0. And let me just get you again in community. So participating in that and having access to simulated LSST-like data in the Rubin Science platform is something that would be useful to you. Keep an eye out in the community forum for an announcement. It's going to be a while. It's going to be next year for more people to come and participate in Data Preview 0. You can find a lot of topics and a lot of information about DP0 in that link I just put in the chat. Right. Or yeah, you can ask Mariano as well, because he'll know all about it. Sure. Mariano, another question?
Yes, there will be next data previews with the not the final camera, I don't remember the name, the temporal camera that we will put in on the Rubin's telescope next year.
Yeah. So Data Preview 0 will be followed with Data Preview 1 and then Data Preview 2.
Right, but when the real data will come from to the data preview.
Yeah, so Data Preview. Data Preview 1 will be sort of late 2022, maybe early 2023, and it's the commissioning camera or ComCam, which just has like a single, what we call a raft, like a single set of CCDs in it. So it's like a very small version of the LSST science camera. So there'll be data from that coming 22, 23, and then data preview 2 will come after that, and it will be images actually obtained with the real LSST science camera as part of commissioning as well. And so that you're sort of looking more at 2023 into 2024 for data preview 2.
But it's good to know because we should comes from simulation the data to the real ones in these 2 years. This is good to know the timeline.
Yeah, and it'll sort of just keep increasing in terms of size and complexity and getting closer and closer until like the first data release will be late 2024, maybe early 25 now with the delays due to COVID. I'm not sure, but yeah, that's sort of what the data release schedule looks like over the next couple of years.
Okay, thank you.
I have a question for about the photometric redshifts. I mean, the strategy to determine photometric redshift and that the measurement and all that details are in one of the Rubin collaboration, or is part of the survey strategy that you are defining now? How are you going to manage that?
Yes, so for photometric redshifts, sort of like 2 things are happening. One of them is, again, desk is the answer here again, because they're developing many different types of photo-Z estimates that are particular to the type of dark energy science that people need to do. So there will be, if you're a desk member, there will be photo-Z catalogs that come from desk that desk members will use for their different science goals. On the Reuben side, as a Reuben data product, there will also be a photometric redshift, like at least one from one type of algorithm in the data release catalog. And so that will be some kind of general use photo-Z, because it's something that many people have a need for, and there's a wide variety of science that needs a photo-Z. So Reuben right now is in the process of figuring out what the science community, as a very broad, diverse community, needs from that one single photo-Z that Reuben will produce. And we are actually there's an open call right now for like letters of recommendation from anyone in the science community to describe what they need from that photo-Z that will be in the data release catalog, or to say, oh, I think this particular estimator would be really good to produce photo-Zs for all the users of Reuben. So those are sort of the 2 tracks for photo-Z that are coming, but it's the Reuben one that will be in the data release catalogs that will be available for all users. And that's the one that we're trying to gather community input on how to make it.
Okay. Thank you.
Maybe I could, again, go to the community forum. There's under science, there's a subcategory for photometric redshifts. And there you will find the call for letters of recommendation for community input on what the Reuben produced photo-Z should contain or how it should be made. And those are due at the end of the month. So we're looking for anyone in the science community to sort of provide letters of recommendation. There's a couple examples here. And if you're really interested in the details of photo-Z, there's a single document that's the roadmap to photometric redshifts for the LSST object catalog. So that's like a roadmap of making all of the decisions, validating the photos that go in the data release catalog, what that all looks like is available in this data management tech note. And something I've been working on for basically since I joined Rubin Observatory. So yeah, so if you have any more questions about PhotoZs, you can definitely direct them to me.
Okay, thank you. Yeah, I think the requirements that we need is more or less similar to the BAO sign case, because they work in large scales, in the large scale structure, and I think that we are going to need to determine voids in that scales also, in very large scales. So I think the science using voids to measure dark energy, it's more or less similar to the case of measuring with the BAO peak in correlations. I think the requirements will be very similar, but I'm going to check all of these that you mentioned. I'm not sure if I'm ready to recommend something, but anyway, I will check it. Thank you.
Yeah, even if you don't feel ready to recommend something, a letter of recommendation can actually just describe the science that you want to do with the PhotoZ. So even if you're not sure which kind of algorithm would be good. So for the first example here is like just a science use case for the PhotoZ. So that's also something that we need to know, like what quality of PhotoZ, like minimum quality you need to do your science, what kind of output parameters, and then we can at least use that so that when we're considering the different algorithms, we at least have a better understanding of your science needs. Yeah.
Okay, so just describe what I need and not to be too greedy.
yeah, not to be too greedy,
Okay.
but yeah, that's sort of the minimum thing that you would be able to use so that we can make sure we at least hit that. Yeah, so you see, it can be very short as well, just a short statement about your science needs for PZ.
Okay. Thank you, Melissa.
Yeah, thanks.
Thank you. Very nice talk, and very useful for us.
Well, I hope so, yeah, and I think you'll get Federica talking to you next week, and she'll have even more useful stuff. And it sounds like inviting some people from Desk might give you like even more useful stuff as well.
More questions or comments? I'm going to stop the recording.